All right, everybody. So we're going to be looking at max, min, and concavity when it comes to exponential and logarithmic functions. So example 1 is also the only example. Given the following equation, y is equal to x e to the x, find the max, min, concavity, and inflection points. So this is all the same process as when we've done curve sketching in the past. We're just using exponential functions this time. So we're going to start by finding the first derivative so that we can do our max and min and our intervals of increase and decrease. So our first derivative is going to be dy dx is equal to, so we're going to be using product rule here. So we've got our f and our g. So the derivative of f is just 1, the derivative of x is 1, times e to the x, plus x times the derivative of e to the x, which is just e to the x. Man, that one's nice. And so we get our dy dx is e to the x plus x e to the x. Okay, that was actually pretty simple. So now we're going to want to get our critical numbers so we can determine our max and min points, our transitions between our intervals of increase and decrease. So our critical numbers, we have 0 is equal to e to the x plus x e to the x. So if we factor out an e to the x here, we get e to the x times x plus 1. So we've got two possibilities. Either e to the x equals 0, which is impossible. E to the x is never equal to 0, because even if we put e to the 0, that's 1. So this one has no solution. So no critical numbers from there. Or we have x plus 1 equals 0, which we do know has a solution, x being equal to -1. So we're going to use that in our table for our intervals of increase and decrease. So I'm going to break this down from -infinity to -1, and then from -1 to infinity. We have e to the x and x plus 1 as our factors. And we're going to use those to figure out where y prime is positive and where it's negative. And then, of course, that will tell us where y is increasing and where y is decreasing. Sorry, I'm just going to fix these lines because it's bothering me. And now that's bothering me. Don't worry, we're going to get there in the end. Eventually. All right, so the first one's actually really super easy. E to the x is always positive. Basic exponential curve, it's always positive. So e to the x is always positive, either of those intervals. X plus 1, on the other hand, from -infinity to -1 is negative, and from -1 to positive infinity is positive. All right, so positive times a negative, what we get, nope, that's the wrong pen, is that the derivative then is negative. Oh, that's a really thick pen. That was unnecessarily thick. Negative and positive. So that means that we are decreasing over this interval and increasing over this interval, which means, oh, it's because I'm using the marker, not the pen. It's all coming together, guys. That's not what I meant to write. That, since we're going from decreasing to increasing, means that this must be a local minimum. Okay, so we're going to look for our local min, local max. So we've got a minimum at x equals -1. And if we go back to our original equation, when x is equal to -1, y will be -1 e to the -1, which is just -1 over e. And for local maxes, none. We don't have a local max. All right. Now we get to our next part. We're going to be doing our second derivative now. So second derivative, we'll just take the derivative of our first derivative. So we get that the second derivative with respect to x is going to be e to the x. So we're just going to be following just regular old derivatives here. The derivative of e to the x is e to the x. Then we have to do product rule on the second part. But the second part is exactly the same as the first derivative we took. So that's just going to be 1 times e to the x plus x e to the x. It's just a repeat of the first derivative. So then what we have is this is, I'm just going to factor it right away. We're going to be having two e to the power of x's and an x e to the x. So I'm just going to factor out an e to the x right away and have this as 2 plus x times e to the x. All right. So now we've got our second derivative. We're going to look for potential points of inflection. Okay. So what numbers are critical to us this time? So our critical numbers here is when 0 is equal to 2 plus x e to the x. And yet again, we have two options, when e to the x equals 0, which of course has no solution, and when 2 plus x or x plus 2 equals 0, same thing. I just like writing it as x plus 2. I don't know why I wrote it as 2 plus x to begin with, but I'm too lazy to go back and change it. So that's something we're all just going to have to live with. Mostly because I'm the one making the video, so it's up to me. So concavity then, we're going to do the same thing we did for finding our intervals of increase and decrease to find our concavity. We have our intervals from negative infinity to negative 2, and from negative 2 to infinity. We are going to be looking at our two factors for our second derivative, e to the power of x and x plus 2. This will give us information on the whether we're increasing or decreasing for our second derivative, and of course whether whether we're positive or negative for our second derivative, and whether we're increasing or decreasing for our original function y. So what we've got is that, yet again, e to the power of x, it's positive in both cases. But x plus 2 is negative from negative infinity to negative 2, and positive from negative 2 to infinity. That means that our second derivative is negative over the interval negative infinity to negative 2, and is positive over the interval negative 2 to infinity. Since positive times negative is negative, positive times positive is positive. That means that over the interval negative infinity to negative 2, we are concave down, and over the interval negative 2 to infinity, we are concave up. Meaning we've got ourselves an inflection point right there, a transition between concavities, between concave up and concave down. So I meant to leave myself a little more room here at the bottom, and as usual, I didn't, because that's just how I roll. There we go. So we can find our inflection point when x is equal to negative 2. Because that's that transition point between concave down and concave up. So inflection point happens when x is equal to negative 2. And when x is equal to negative 2, going back to our original equation, remember, always go back to the original equation. The inflection point is on the original graph, not on our derivative graph. So this is negative 2 times e to the negative 2, or just negative 2 over e squared. Okay, so this, I'm going to put a big box with all of our solutions neatly put together. So what we've got here is, we've got, it's asked for our max, our min, our concavity, and our inflection points. It didn't ask for intervals of increase and decrease, but you know, since there's only one max min point, it's actually pretty obvious what our intervals of increase and decrease are. So I'm only going to do what it asked me to do because I want to. Local min then is at negative 1, comma, negative 1 e over e, which we got in the above work that we did. Sorry, I'm not very coherent today, am I? Our local max, there isn't one. No local max. Concave down, our interval of concavity for concave down is from negative infinity to negative 2. And our interval of concavity for concave up is from negative 2 to infinity. And our inflection point is then going to be negative 2, comma, negative 2 over e squared. And that is our answer. Yeah. All done. All right. And that is an example of how you can do curve sketching of exponential functions. Obviously, you could then use all this information to actually sketch this curve, and I probably should have in this example, but I'm not. Okay, bye.